Section 27 of the Science History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Andrea Kay. The Science History of the Universe, Volume 1, edited by Francis Rolt-Wheeler. Astronomy. Chapter 19. The Planetoids. In the chapter on the solar system, it has been shown how Titius in 1772 pointed out that if 4 should be added to the following series, irregular in that the first number should be 1/2 instead of 0, 0, 3, 6, 12, 24, 48, a sequence of numbers would be obtained that indicated the relative distances of the 6 planets, with the striking exception that next after Mars there was no representative. Bode filled this gap with a hypothetical planet, and his name is often associated with that of Titius in the statement of this law. After the discovery of Uranus by Herschel in 1781, the law of Titius or Bode, with which this planet conformed, gained considerable respect from astronomers, although no mathematical or other reason was known to uphold the singular relation between the distances of the planets from the Sun. At any rate, the conviction that there must be an undiscovered planet between the orbits of Mars and Jupiter, as was even suspected by Kepler in his Mysterium Cosmographicum of 1596, was strengthened, and accordingly it was proposed by a voluntary association of astronomers in 1789 to undertake a systematic search for the missing planet. An organization was arranged on a fairly methodical basis by Baron von Zach, but before these celestial police, as the astronomers enlisted for this purpose were humorously termed by their organizer, had secured results from their plan of cooperation, the missing planet was found under interesting and somewhat extraordinary circumstances. At an observatory at Palermo, Sicily, Giuseppe Piazzi, 1746 to 1826, had been at work for some 9 years on the preparation of a catalogue of the stars. On January 1st, 1801, he noted an 8th magnitude star, which on subsequent evenings shifted its position and induced him to believe that he had discovered a new kind of comet without tail or coma, and so he described it in a letter to Bode at Berlin. A fortnight later the wandering body changed its retrograde for direct motion, and before the observations could be repeated by other European astronomers, Piazzi's moving star approached too near the Sun to be visible any longer. For its rediscovery, some accurate knowledge of its path was essential. Never before had there been such meager data on which to calculate the motion of a celestial body, for even in the case of Uranus, observations for almost a century had been made and recorded on the assumption that that planet was a fixed star. That the new star was a planet, however, lay outside the realm of consideration. It soon was found that the calculation of its orbit could not be adjusted, for the observations did not harmonize with any sort of parabolic cometary orbit. Then the supposition arose that it was a planet and that it had an elliptical orbit. But how was such a path to be calculated? The case had never yet arisen where a planet which had a relatively rapid motion had been under observation for so short a time, and the orbital velocity of which was unknown. Men of the hour were not wanting, and a brilliant young German mathematician, Carl Friedrich Gauss, 1777 to 1855, of Göttingen, now entered the ranks of astronomy. He computed the orbit of the new body with remarkable skill, and in November of the same year presented his conclusions to the observing astronomers. It was only on the last night of the year that the sky was sufficiently clear for good seeing. At the Gotha Observatory, almost in the very position assigned by Gauss to the runaway planet, a strange star was discovered which filled the gap in the series of Titius, and in the following year, March 1802, at Bremen, Dr. Heinrich Olbers 1758 to 1840, also observed a similar star. The first of these, at the request of Piazzi, was named Ceres, after the protecting divinity of Sicily, while the second, which furnished an additional problem for Gauss, was named Pallas. Harding, the assistant of Schroeder at Lilienthal, discovered 1804 Juno as the third, and Olbers 1807 Vesta, the brightest of all the planetoids, as the fourth, all lying between the orbits of Mars and Jupiter. There were thus, in contradiction to the law of Titius, instead of one planet, 4 present in the zone between Mars and Jupiter. They were designated asteroids by Sir William Herschel, though the more modern term planetoids is to be preferred. Thus was inaugurated the discovery of minor planets, which continued during the 19th century and is still in progress. Where one new planet might be anticipated according to older doctrines, many were found. Various theories have been advanced to explain their existence and occurrence. That Ceres and Pallas were parts of an exploded planet was an ingenious theory which received for a time considerable acceptance, but which was disproved by Professor Newcomb. The recognition of the minor planets became of the highest importance in astronomical science, and led to the construction of star maps and to further interest in the observations of the heavens. The discovery of the fifth planetoid did not occur for a number of years, and then fell to the lot of an amateur astronomer, Postmaster Henke at Dresden, who was industriously searching with his telescope the quarter of the sky lying opposite the sun. He made a practice of mapping all the little stars and of comparing them again on the following nights. At last, 1845, he found a new planetoid, to which he gave the name Astraea, and in 1847 a second, Hebe. Since then no year has passed without the discovery of one or more new planets. This may be attributed not only to the example of Henke with his systematic industry, but also to the perfecting of the telescope and to the publication of printed special star charts upon the basis of the localizations of numerous fixed stars. Thus by the year 1868 the number of little planets had increased to 100, in 1879 200, 1890 300, 1895 400, 1903 500, 1906 600, 1907 700, 1908 800. Consequently, instead of one looked-for planet, suspected by Kepler, a complete stream is present between Mars and Jupiter, as indicated in Figure 26. The zeal of astronomers was directed toward the observation of the numerous newly discovered heavenly bodies, and the most fortunate discoverers achieving success in this field were Hind at London, Goldschmidt, an amateur, at Paris, Gasparis at Naples, Robert Luther at Bilk near Dusseldorf, Chacornac and the brothers Paul and Prosper Henry, who discovered at Paris during the construction of stellar charts of the zodiac a number of planets among the numerous charted small fixed stars, and from the United States Watson at Ann Arbor and C.H.F. Peters at Clinton, who astonished the world by their numerous discoveries. Johann Palisa should be named above all. While director of the observatory at Pola, he discovered 83 new planets, the majority with a small telescope. Later he moved to Vienna, where large refractors were available. The number of small stars now becoming visible changed the accustomed groupings, and thus hindered rather than favored the further discovery of new planets by him. In Vienna, however, he made himself especially serviceable by following up the faint planets already discovered. Certain orbits of the minor planets are shown in Figure 26, all of which are described in a standard or west to east direction. At the Lick Observatory, Mount Hamilton, California, in 1894 and 1895, Professor E. E. Barnard made a series of direct measurements of the 3 largest of the minor planets, obtaining for the diameter of Ceres and Vesta 405 miles for each, and for Pallas 322 miles. The size of these minor planets compared with the Moon is shown in Figure 27. The planetoids in the aggregate do not bulk very large, for we know from the calculations of the distinguished Leverrier, who studied the perturbations of Mars, that the total mass of all known or unknown bodies between Mars and Jupiter cannot exceed a fourth that of the Earth. Later knowledge derived from light observations would place the total mass of those already known at many hundred times less than this limit. If the combined mass were as great as 1/100th the mass of the Earth, it would produce perturbations in Mars, of which there is no evidence. B. M. Rossell in 1895 estimated that the terrestrial globe contains 3,240 times the aggregate mass of the first 311 minor planets. In December 1891, Max Wolf at Heidelberg began that photographic observation and discovery of the little planets, which has resulted in rich gains. Repeated and long exposures of the photographic plate are made, an equatorial telescope fitted with a camera being directed at some point in the heavens and kept there by means of clockwork. Consequently, the fixed stars register themselves upon the plate as points, and the moving planets as short faint streaks, which are discovered by means of the microscope after development and fixing. In this way, more planets have been discovered in Heidelberg since 1892 than by all previous observers together. Charloy at Nice emulated Professor Wolf in applying the photographic method, so that there has developed since 1892 with great success a new field of astronomical photography. An American astronomer, the Reverend Joel Metcalf at Taunton, Massachusetts, has improved the technique of observation. In 1905 he found 2 and in 1906 12 new planetoids. Since 1892, newly discovered planets have received provisional designations of the letters A, B to Z, AA, AB to AZ, BA, etc. to ZZ, and with the number of the year preceding. If it has once been established that they can be observed sufficiently long to guarantee finding them again, and that they are identical with none of the earlier planets, they receive the next numeral and name, and are thus included in the system. In this manner, an unnecessary increase in the lost planets of the system is avoided. In 1907 the crucial moment came in which the planet ZZ was discovered, and the series of provisional designations began again. Up to 1896, all the 432 planetoids moved in the zone between the solar orbits of Mars and Jupiter, and indeed all with the same right-handed motion. Consequently, no little attention was attracted when on August 13, 1898, Witt, at the Urania at Berlin, photographically discovered a planet with an unusually rapid motion. The computation of its orbit showed great proximity to the Earth, and a mean solar distance of 1.46 times the distance of the Earth, hence less than that of Mars, 1.52. Was this celestial body to be counted in with the stream of planetoids between Mars and Jupiter? Since the possibility existed that still other planets might be discovered which were not confined to the zone between the orbits of Mars and Jupiter, it was determined to include it with the planetoids with the numeral 433, but to distinguish it by the masculine name Eris. The orbit of this planetoid was found to lie in that forbidden territory within the path of Mars and between it and the Earth. With the single exception of the Moon, it is the nearest large heavenly body to the Earth. This little planet, hardly more than 20 miles in diameter, in addition to its anomalous position, possesses remarkable characteristics, among them an orbit of great eccentricity, which causes it to be at aphelion some 24 million miles beyond the mean distance of Mars. An examination of Figure 28 will reveal how very interesting its orbit is, for on the rare occasions on which the planetoid comes nearest to the Earth, it is closer to the Earth than Mars or Venus can ever be. Furthermore, this little planet not only is variable, but varies in its variability, which has given rise to the assumption that either rapid changes are taking place on it, or its light reflecting power varies with its position as regards the Earth and Sun, as might be the case if the planetoid were really double, with two components revolving around a center of gravity, or if the body itself were unequally reflective in its various parts. The mean distance of Eris from the Sun is 135 million miles, but at aphelion it is 165 million miles away. Its perihelion distance is only 105,300,000 miles, or about 12,400,000 miles greater than the mean distance of the Earth. On account of the large inclination of the plane of its orbit to the plane of the ecliptic, Eris never approaches the Earth nearer than about 13,500,000 miles. These near approaches occur only when Eris is in opposition at its perihelion, which unfortunately happens rarely. Its sidereal period is 1.76 years, from which it follows that its synodic period is 2.32 years. If an opposition occurs at perihelion, then in 37 years another will occur very nearly at perihelion, for 37 is almost evenly divisible by 1.76 and 2.32. The next most favorable opposition will occur in 1931 and will furnish an unexcelled opportunity for obtaining the solar parallax. Because of its eccentric orbit, Eris acquires a highly practical significance in respect of the determination of the true size of the entire planetary system. From the laws of the orbits is found, in fact, very accurately, to 6 decimal places, the relations of the planetary distances. On the other hand, these distances themselves are very little known. They are inversely proportional to the solar parallax, 8.80 seconds, of which one can be confident of but 2 decimal places. We have already seen that by means of observation of the transits of Venus, observation of the nearer planetoids and of Mars, determinations of the velocity of light and of the parallactic lunar equation, great pains were taken in the last century to ascertain with more exactness the solar parallax, and thus the extent of our entire planetary system. It appears that the observation of Eris yields this quantity with 3 times the exactness of the earlier methods, and that nothing else than the observation of the lunar orbit for the determination of the parallactic equation can compete with it. Thus the discovery of Eris performed a useful service for astronomy. 2 months after the discovery of Eris, Wolf, still at Heidelberg, discovered the planet Hungaria, number 434. This, next to Eris, is, with its solar distance of 1.94 units, the innermost planet of the stream. Its orbit lies, however, entirely in the zone beyond the orbit of Mars. Just as Eris goes beyond the zone between the orbits of Mars and Jupiter toward the inside, so 3 lately discovered planets do so toward the outside, though, to be sure, to only a small degree. These have also received masculine names. Highly theoretical investigations have been carried out by Hansen, Glyden, Poincaré, and Sir George Darwin, which have gained from orbital computation continually new points of view and have led to beautiful mathematical ideas. Here belongs the question of the simple relations of the times of revolution of a planet and of Jupiter as the most important disturbing planet, or the so-called libration of the orbit, as it comes to light in some measure with Hecuba, number 108, and with planets of the Hecuba type. The value of the little planets is thus not to be sought upon the practical, but rather upon the theoretical side. But the trouble and time which hundreds of planets uninterruptedly required for their rediscovery and the correction of their orbits was so considerable that the question arose whether the gain was worth all the trouble. So, in the 80s of the 19th century, a number of astronomers demanded that a choice be made of the planets, and that only a part be followed up with accuracy, and that the rest, since indeed they apparently showed merely the same phenomena, be abandoned without attention. This would hardly have lessened the labor, For, since the discovery of planets could not be prohibited, the majority of the planets would have been lost and would be continually discovered over again. Professor Tietjen at Berlin found a middle course. Since 1891 he abandoned the yearly ephemerides, tables which give the course of the planets during the entire year, and stated merely in one line for each planet time and place of opposition and the daily variation in its position. For selected, important, and interesting little planets, opposition ephemerides were printed, which gave the position of the planets daily with exactness for 6 weeks of their best visibility. The majority of the planetoids appear as mere points and are immeasurably small. However, Weiss estimates, on the basis of brilliancy, the largest of them at 342 kilometers (212 miles) and the smallest at 16.14 and 10 kilometers (10 and 6.2 miles) in diameter. There is no doubt that many small bodies are in motion among them whose diameters are of 1 kilometer (3,281 feet), of perhaps 1 meter (39.37 inches), and even of 1 millimeter (0.039 inch), and that the majority, on account of their faintness, are not visible to Earth. The planetoids are of no immediate use to mankind. Their orbital calculations can be used neither for the determination of time nor for the guidance of mariners. But the ideal beauty of these planets is that their reappearance is continually a test of the correctness of mathematical assumptions, and that they exhibit over and over again the validity of Newton's law of the universal attraction of all bodies. End of section 27. Recording by Andrea K.